I'm starting, got it. Okay, we are alive. So continuing the National Observatory seminars, it's a pleasure to have here Professor Hector Marin from University of Barcelona. Hector did his PhD on Barcelona and had some postdocs in Portsmouth, in Paris, and now he's again in Barcelona for a postdoc. And Hector has been developing very interesting work on how to extract information from large-scale structures. So it's a pleasure to have you here for the seminar. Hector, you can start.
Well, thank you very much for having me. So today I'm going to be talking about model-agnostic analysis of spectroscopic data, but in particular focused on the already publicly available data sets, which are BOSS and eBOSS. So I'm just going to, this is the outline of my talk. So for those that I'm not very familiar with the topic, I would make some introduction on spectroscopic surveys, on what baryon acoustic oscillations and redshift space distortions are, and also on these publicly available data from BOSS and eBOSS. And then for more technical oriented people, then I will talk about this compression technique called ShapeFit, and then its application to BOSS data, showing you some cosmology results. And in the end, I will also talk about how this new technique can help us to shed light on the current Hubble tension. So from the large-scale structure point of view, you have essentially two main sources of information. One is the CMB. CMB, it's essentially very early time physics. Physics there is quasi-linear. The amount of information is not super large, essentially because it's two-dimensional surfaces. It doesn't have depth. It's just something that happens at a certain time. But then we have already been exhausting the amount of information in these primary anisotropies by the observation of WMAP and Planck. So in that sense, the information in terms of primary anisotropies contained by the CMB are cosmic variance limited. If we want to keep learning about the universe, then we can look at what happens at later times. This is like tracing the distribution of galaxies, because it's a late time, because the galaxies happen to live at later times, then they are essentially natural sensitive to late time physics. This is essentially dark energy or lambda. They are also contain information from early time physics, as we will see. Some examples is the FNL or the imprinted scale sun horizon. And the complications are that they are susceptible to very non-linear physics. You have to deal with galaxy bias, peculiar velocities, etc., etc. But on the contrary, they are like very large volume. It's a 3D now, it's not just a 2D-dimensional. So the potential amount of information we can extract from galaxies is much larger than from the CMB. So when I talk about galaxies, I would focus essentially on spectroscopic surveys. I would not talk about photometric surveys, which are another source of information. So in terms of spectroscopic surveys, what we are measuring are essentially two things, are angles and redshifts. So in order to make a three-dimensional map out of these angles and redshift, we need to convert redshift into moving distances. And in order to do this, there are essentially two assumptions. We need to assume a certain cosmological model, and we need to assume that the velocities are due to the Hubble flow. So the redshift we are observing, they are essentially velocities, they are due to the Hubble flow. And we will see how these two assumptions essentially may not be exactly true and how we can account for that when we extract information. So along all this talk, I'm going to be talking about how to extract information from galaxy maps, but we have to bear in mind that these galaxy maps are non-deterministic. are stochastic by nature, and therefore we cannot directly infer physics out of the position of the galaxies, but we have to construct statistical tools, and these are essentially the correlation function. So we can work in configuration space and work in terms of the 2-point, the 3-point, or the 4-point correlation functions, or in Fourier space, that they are like the Fourier counterpart. For the 2-point correlation, it's called the power spectrum. For the 3-point, it's called the bispectrum. For the 4-point, it's called the trispectrum. And these are essentially pair countings or triplet countings or quadrilateral countings of galaxies at different scales and at different shapes. So if the galaxy field were Gaussian, all the information would be contained in the power spectrum, the bispectrum would be 0, and the trispectrum would be just a function of the power spectrum. But because of galaxy evolution, even if the initial condition galaxy fields is Gaussian, the principle is not, but imagine that it's Gaussian, just galaxy evolution would cause a non-Gaussian signal that would eventually produce a 3-point function and a 4-point function. So in this talk, I'm just going to be focusing on extracting information from the 2-point function, but we have to bear in mind that going to higher order statistics, it's also possible, and it's another source of information. So let me start with how we extract information from these galaxy maps. One is looking at what is called the baryon acoustic oscillation, or the BAO, and use this as a standard ruler. So for those who don't know, the BAO is a sound wave that it's created at the early times before recombination, when we have a plasma of photons or baryons which are coupled, and then they are oscillating because of pressure radiation. And this oscillation produces waves, sound waves that travels in this medium, and they are traveling up to a certain distance where they cannot travel anymore because the universe has gone through a threshold temperature where this medium cannot exist anymore, and then it's what is called the decoupling, where these waves are frozen, they cannot travel anymore, and they have traveled a certain distance that we are going to be referring as the sound horizon scale. So this distance, sound horizon scale, in principle, is imprinted not only on the distribution of photons that it's later received in the CMB signal, but it's also imprinted in the distribution of baryons that eventually are going to form galaxies. So when we observe the galaxy field, we are also going to be seeing this bump, this excess of probability distribution caused by this excess of density at a certain distance by the sound horizon scale. So using this sound horizon scale distance, we can calibrate our measurements and then help us to convert redshift into distances. So this is how we essentially extract information on the Hubble parameter from galaxies. But even though if we don't calibrate our measurements with this sound horizon scale, just by knowing that it exists and by knowing that it has to be isotropic, we can actually perform some measurements, as I will explain briefly. So under the assumption that the universe is isotropic and homogeneous, any extra anisotropy we measure, we can associate it to an observational effect. And there are essentially two observational effects that create an anisotropy. One is called the Alkop-Peczynski effect. So this effect is the anisotropy is induced by transforming redshift into distances, assuming a reference cosmology which is slightly different from the two cosmology. So this essentially, when transforming redshift into distances, we just assume a cosmology that it doesn't matter the actual value, but in principle, let's say it's different from the actual cosmology of the universe. This creates an anisotropy which is different along and across the line of sight. So we have, I've just put here some equations for those who are maybe more familiar with, but the idea is that if you have like an isotropic structure in your distribution of galaxies, that it can be the BAO, but it can be any sort of feature, transforming it redshift into distances creates an elongated structure instead of having a circular structure. And this elongation happens along and across the line of sight. And this elongation is slightly different because if you do the math, then you see that essentially there are like two dependencies with the cosmologies you have chosen. And essentially by tuning this cosmology and say how far away we are from being isotropic, we can say how away is our reference cosmology from the true cosmology, and therefore we can say something in terms of the information content of the universe. So these two distances, the distances along the line of sight and across the line of sight, I will going to be referring as the h and the m. In reality, because we need to know the exact size of the ruler, and in principle we are not going to assume it, we can say that we express these distances in terms of the unit of the ruler, which is the sound horizon scale, RS in this case. So essentially, by transforming redshift into distances, we can define these two parameters that they are related to the Alko-Paczynski effect, and these are going to be our parameters of interest. So focusing on the BAO, at recombination time, we have the BAO bump in the two-point correlation function, which has a certain distance, which is the sound horizon scale. In the galaxy times, at later time, because of the expansion, we have this BAO distance is the horizon scales times the expansion of the universe. So if we just rely on the uncalibrated BAO, we can just take the ratios between these two distances and looking at how difference is from one, then we can say how different our reference cosmology is from the true cosmology, and this serves as a way to measure the amount of matter, omega matter. We also can look at the isotropic dilation of the BAO, which is essentially, if we assume we know the size of the BAO, which is knowing the RS, then by measuring the absolute size of the BAO in our galaxies, then we can say something about the universe, and this is usually referred as dV over RS of the isotropic BAO distance, whereas the Alko-Paczynski test, which is just the ratio between these two distances, we refer as FAP. So essentially, FAP measures the m, dV in terms of the sound horizon scale, in combination with FAP measures the Hubble parameter, or the expansion of the universe at the time of the observation, times the size of the horizon scale. So this is like the interpretation of these two quantities under the lambda CDM. So there is another source of anisotropy, which is caused by redshift space distortion. And this is essentially because we assume when we transform redshift into co-moving distances that the galaxies are moving along with the Hubble flow. But in reality, we know this is not true because galaxies attract to each other. So there is a component in the redshift we observe, which is not caused by the Hubble flow, but by the peculiar velocities. And this essentially creates this elongated pattern across the observer that you might be familiar with, which is called redshift space distortions. So essentially, if we have an observer here and we have our line of sight along this direction, a certain distribution of galaxies that would look isotropic. This is some circular feature stuff because of the peculiar movements towards the center of each of these galaxies makes us look like as if their positions were a bit squashed along the line of sight at large scales and elongated along the line of sight if we go to smaller scales. So this inconvenience, it's actually kind of helpful because the actual infall velocities of the galaxies are related to the amount of matter in the universe. So by measuring the excess of squashing, we can put constraints on what is called the logarithmic growth of the structure, or F parameter, that is related to omega matter. So in reality, in order to capture this anisotropic feature, we can think of the power spectrum in terms not only of the scale by the angle, but the angle of the line of sight of our observation with the vector of the galaxy pair. So this is usually called beta, and the cosinus of beta is called mu, which is usually referred to as the line of sight. So now our power spectrum, which is itself anisotropic because of Redshift space distortions and because of Alko-Paczynski is not only characterized by scale or the wave vector k, but also by mu. And instead of working in terms of a beam power spectrum in terms of k and mu, we prefer to make an expansion around Legendre polynomials, which is an orthonormal base in this space. And then each of these Legendre polynomials has an associated amplitude that we refer to as monopole, quadrupole, and hexadecapole. And instead of working in terms of pk mu, we are working in terms of p of k for the monopole, for the quadrupole, and for the hexadecapole. Being the monopole, the natural isotropic signal, and being the quadrupole, the hexadecapole, and we could even go to higher orders, the anisotropic signal. So if we take just as a toy model the Kaiser linear term, which is the linear model that explains redshift space distortions, we can simply work out how these monopole, quadrupole, and hexadecapole are going to look like in terms of certain galaxy linear bias parameters or this growth of a structure F. And we see here that essentially this is the matter linear power spectrum times a boosting factor, which is different for each of these multiples. And because this signal is different, then we can break the generacies between the bias and the growth factor F. However, we have to bear in mind that there is another intrinsic nuisance parameter, which is the amplitude of the linear power spectrum that we can characterize this as sigma 8. And we see here that because sigma 8 is also a not known parameter, when we put this here sigma 8, then we don't have access to the bias or F. Instead of, we have access to the growth of a structure times sigma 8 and to the bias times sigma 8 as natural parameters. Of course, if F is known by assuming that we know M and we believe in GR, then this degeneracy between F and sigma 8 can be broken, and then through redshift space distortions, we could measure sigma 8. So far, I have been describing these three quantities. They rely on the Alko-Paczynski parameters applied to the BAO, which is the distance along the line of sight, the h, and across the line of sight, the m, in terms of the units of the sun horizon scale, Rs. They are related to cosmology parameters through these integrals, and redshift space distortions allow us to constrain this combination of parameters f times sigma 8. So essentially, the information content flows in this way. So we have our raw galaxy maps. They are compressed in terms of summary statistics, namely the power spectrum. From the power spectrum, we extract these three variables per redshift bin. And assuming now a cosmology model, we can interpret these three variables and say something about the cosmological parameters of lambda CDM or extension models, gravity, inflation, etc. So this is how the large-scale structure analysis was done in the official BOSS and eBOSS analysis. But then we can ask ourselves why we need this intermediate step here, if maybe we can just directly interpret the size and the amplitude of the power spectrum and directly forget about this intermediate step and constrain cosmology parameters directly from the power spectrum. So this is what has done by some of the papers. So now in the literature, we have these two ways of analyzing the power spectrum. One, which I would be referring as the standard way, which essentially uses a fixed template and modifies this fixed template according to a certain physical quantities, essentially the BAO distances along and across the line of sight, and the rest is the distortion parameter of f sigma 8. And it aims to constrain these things, and then later can be interpreted in terms of the cosmology parameters such as omega mater A square, AS, etc., etc. The other analysis, which I would be referring as full modeling, it's more like how CMB analysis does, a CMB team does his analysis, which is essentially you take a linear Boltzmann code that generates a linear power spectrum, then you apply certain non-linear corrections to apply for the interactions between galaxies, you put bias parameters, etc., and you directly infer these parameters. So then you can ask yourself, what are the difference between these two models? And if there is any extra information captured by this guy instead not captured by this guy. So these are like these two ways of actually doing the analysis. So if you are more observational oriented, what you want to do is to actually extract the physical features from your data, and these physical features from large-scale structured data are naturally this set of parameter compression that I have defined before. If you are more theory-oriented, you say, oh, I don't care about the data. I have my theory model. I'm going to directly construct the observable from the data, which is the power spectrum, and I'm just going to directly fit the the parameters of my model, which is like lambda CDM, nu lambda CDM, k lambda CDM, whatever model you choose. So this is like two ways of doing the analysis. That you start from linear physics and you go towards nonlinear physics, which is what CMB does, or the other way around. It's like the standard analysis is more like what supernova people do, is like, let's look at some observable from our data. So in order to bridge these two approaches and see whether they are consistent or not, we did some studies in this paper along with Samuel Briden, who was my student at the time. So essentially, we took these two approaches and we fit the data and we observe how the results look like. And for instance, in this parameter space, we just assume certain priors on some nuisance parameters which are not constrained by large-scale structures, such as baryon density, NS, or the amount of neutrinos, and we just varying sigma 8, H, and omega matter. And this is what we obtained. So if we were doing this full modeling fit, this direct fit to the power spectrum in blue, we get like a very tight constraints around here. Whereas if we do the BAO plus RSD analysis, we get this orange constraint here. So you see that the amount of information that it's contained in these two approaches, it looks very different. And this was some striking questions we had at that time. It's like, why this is so different? So in order to look at why this is so different, we just can look at this star here in parameter space, and then we can look at how the power spectrum look like, and we will see why this is a good fit for BAO RSD and why this is a bad fit for the full modeling stuff. So we also realized is that when these two analyses were combined with Planck data, then the two models were not so different. They all were giving the same constraints. So this also gave us some hint on where the extra information could be coming from, and it's actually in the transfer function. So in order to fix or complement the standard analysis and make it look like in terms of information content, like the full modeling analysis, then we proposed a modification of the template through another couple of variables. So in order to do this, we now parameterize our template power spectrum in terms of the true power spectrum with this modification. So before, this ratio was only changing because of the because of the BAO distances along and across the line of sight and through pressure space distortion or F sigma A. But now here we are choosing an extra set of parameters, which is, it looks like a sigmoid in K space. So we parameterize essentially this with this functional form where A and KP are chosen to be fixed at these values. It doesn't really matter much which values do you choose, but for lambda CDM like models, these values seem to work well. And then M1 and M2 are free parameters of our models that in principle complement the BAO distances and the pressure space distortion parameters. So the sigmoid function was capturing very well the variations on omega matter and omega baryon and on NS. that was affecting, and in principle were not captured by the standard model. And as we will see just before, this M2 is very similar to what it's called NS, the spectral index in the lambda CDM scenarios, and M1 is very similar to omega matter H squared. So we also observed that for current publicly available data, these two parameters are actually very degenerate. So if you try to constrain both at the same time, you will not get much information out of it. So in all my analysis, I would essentially fix this M2 or NS to a fiducial value that I assume to be known. And I'm just going to be focusing on what's the extra amount of information coming from M1. So just to sum up, if you want to express your information content in terms of compressed variables, the standard analysis, the standard BAO analysis tells you that there are these two BAO distances in terms of the sound horizon scale, which are related to lambda CDM variables, which are like omega matter coming from the ratio of out of it, or H times Rs. If you take each of them independently, then you have standard Rsd analysis, which is essentially F sigma 8 in terms of compressed variables, which tell us something about the actual amplitude, or sigma 8. If you know omega matter, then you can infer F, and from F sigma 8, then you can get AS. And finally, in order to complement this, you can add this extra parameter, or this ShapeFit parameter, M, that I just described before, and this tells you something about omega matter H squared if you assume certain priors on omega baryon and on the spectral index. And this full set of now 4 parameters now complement very well the information from the power spectrum. So in this plot, you see here how these two variables are very complementary. So geometry and growth, essentially these 3 sets of variables, BAO and F sigma 8, they put constraints on RD in terms of megaparsecs over H. So actually H times RD in megaparsec units, which is this line here. And the slope, or the M shape, it complements very well a very bad quantity measured by these 3 guys, which is omega matter H squared. So in combination of these two, now our parameter space is super good constraint, and it's actually in very good agreement with the full modeling. So again, here I'm just comparing how the cosmology inferred from these 4 set of variables in green look like in comparison with the actual fit to the power spectrum. And now you see how similar these different analyses return essentially the same information. So now you see that this set of 4 compressed variables is lossless in terms of information content with respect to the natural lambda CDM variables, at least for analysis where you have a prior on omega baryon and where you have an S fixed or an S with an actual prior. So now we have complemented this information flow, and we have this set of 4 parameters. So just for the aficionados, and essentially if you are familiar with all this formalism, so ShapeFit, or adding this extra M shape function, is just a compression technique. You still need to assume a perturbation theory model to account for the nonlinear galaxy power spectrum. So in particular, for this work, we are going to be assuming that we model this through the Rasan perturbation theory at 2 loops, and redshift space distortions are accounted from this known TNS model. But these are just details. So if you're not familiar with those, don't worry, it's not very important for what I'm going to say. But essentially, if you have another favorite perturbation theory model, you still can substitute and apply ShapeFit, which is just a compression technique. It's not a perturbative, it's not a theory model. But yeah, so also in terms, apart from these 4 variables, I'm also going to be constraining galaxy parameters, which are nuisance to me. So I just need to marginalize over them just to account for the complex galaxy physics. And in this case, I'm just going to assume a first order and a second order bias parameters. an amplitude for the shot noise, and a parameter that regulates the thickness of cut. So before going to how it looks to the data, we actually ran a blind challenge in order to quantify our systematic error bars. So there was this publicly available data by Takahiro Nishimichi. It's in this link. So we download the measurements of the power spectrum, and then we try to infer 3 not known parameters, assuming lambda CDM model. So these parameters were omega baryon, AS, and H. So we ran our ShapeFit analysis on these models, and then we submit our results to Takahiro, and then well, essentially we got it quite well. Here I'm just presenting the results in terms of the effective volume of this blind challenge, which is very, very large. It's much larger than the typical volume of surveys. And you see here how the actual deviation with respect to the true values that I'm not showing because it's still a blind challenge. So I'm just showing deviations with respect to the true values, which are shown in these vertical and horizontal lines. You see how the results from the ShapeFit, they are very close to each other, and they are also very similar to those coming from the actual full modeling. So if you are worried about these small deviations, you have to bear in mind that your statistical values of a survey realistic, such as the eBOSS DR16, which is like 11 gigaparsecs, they look very much larger than these small deviations. So just for comparison, I'm seeing here the typical size of the errors you would get from an actual survey in green compared to the actual maybe systematic component, which is like really subdominant. So we are happy. We have a model that works. We have a model that contains all the information, just applied to some publicly available data. So the most accurate data, or the largest spectroscopic maps we have right now is BOSS and eBOSS. They cover a large area of the sky of around 10,000 square degrees between the northern and the southern galactic hemisphere. And it's essentially covering a wide redshift range, going from galaxies, very nearby galaxies, up to very distant quasars, up to redshift 2.2. And in total, there are almost like 2 million objects. We also have another source of information, which is the Lyman alpha emission lines, which are like even beyond quasars, that we are also going to use, but we are just going to be focusing on the BAO case. We are not going to be running redshift space distortion or shape information in Lyman alpha. So this is another nice picture how to summarize the results from SDSS. So as I've said, we should be here in the center, and then as we go back, we have the CMB time here, and then intermediate we have several population of galaxies. So the closest galaxies, we have a sample of bright galaxies. For this study, we are not going to use it because it's not very relevant. But then from redshift 0.2, we start seeing nearby LRGs, or luminous red galaxies, that they extend up to redshift around 1, where they decay, and then we have quasars which stand in this intermediate region before this Lyman alpha forest. So yeah, this is like a nice picture of visualizing. And here in this plots, just for visualization, we've plot the detection of the BAO peak. So in this case, I'm just going to be using the LRGs, not going to be using the bright galaxies because they are not very large sample and they are not adding much. We are not going to use the ELGs. It's just, again, a very small sample, is barely BAO detected. And for the Lyman alpha, we're going to use it, but just in terms of the BAO. So this is our results, how they look like in terms of the monopole signal, the quadrupole signal, and the hexadecapole signal. The different colors are different galaxies at different redshifts. So in red, orange, and green, we have LRGs spanning from redshift 0.2 up to redshift 1. And from redshift 0.8 to 2.2 in blue, we have the quasars. We're using a larger K range in quasars because physics at larger redshifts is more linear, and therefore our model stands up to larger K values, as there's more scales. We are also going to use some information coming from the reconstruction, which I haven't mentioned here, but essentially there is a post-processing of the maps that allow us to extract BAO information more efficiently. And as I've said, in addition to this, we are going to be using BAO information from the Lyman alpha at very high redshift. So for each of these redshift bins, we are going to be constraining essentially these 4 compressed parameters, which are DH in terms of RS or RD in this case. This is like the same units. So BAO along the line of sight, BAO across the line of sight, F sigma 8 and M. And these are like 4 set of correlated parameters per redshift bin. In case of these 2 first redshift bins of galaxies, they are also correlation between, because these 2 bins are overlapping. You see that this bin ends up at 0.5, this starts at 0.4, so there are like some overlapping between galaxies, but we will account for this correlation. So per redshift bin, we have 4 parameters, and then these 4 parameters per redshift bin. So 4 redshift bin, 4 parameters, 4 times 4, 16, plus 2 BAO parameters, 18 parameters at different redshifts that we can reinterpret in terms of a chosen model. If you choose the standard raw lambda CDM, where just 3 parameters, which are H, omega matter, AS, you need to put constraint. You have to put external priors on omega baryon and on NS, then you get these constraints. And in blue, you have the full information coming from the full set of 4 parameters per redshift bin. And in green, you have what you had before, so not using the shape. So essentially 3 parameters per redshift bin. So here you can visualize very well how the shape really helps to get constraints on H and to get constraints on omega matter. And actually in omega matter, we are using information on the amount of baryons coming from Big Bang nucleosynthesis and fixing NS to the fiducial value of Planck. Then we get an error bar on omega matter, which is even better than the Planck precision. So we are measuring omega matter very, very well. And we get also a very decent and well measured H0 value, and also sigma 8, or which is correspondence to AS. So we can do this exercise of reinterpreting these 4 models for different models of cosmology. So not just for the vanilla lambda CDM, but for a lambda CDM where the neutrinos are varied, another with some sort of dark radiation or an effective, open, W lambda CDM, WA, W naught lambda CDM. And this reinterpretation of parameters in terms of the new model is very, very fast. So you don't really need to redo any analysis, because all these different models, they share the same set of compressed parameters. And this is why our analysis, we call it agnostic, because what we are doing, we are extracting physical features from the actual maps that they don't have anything to do with any actual cosmology assumption. So these measurements are essentially independent of the model. And then once these are measured, then there is this interpretation of what these parameters means in terms of a certain model. So just very quickly, I'm just going to go through these different models. So for instance, the neutrino or lambda CDM, or essentially where some of the neutrino masses are varied. So I'm showing here some constraints. So in green, without the standard analysis, without the shape, with the prior and omega baryon coming from BBN, you get this very loose constraint on the sum of the neutrino masses that essentially are very uninformative. And just by adding the shape parameter, we get the blue constraints. They are not striking, but now you are seeing actually some decent measurement of the sum of the neutrino masses, which are like start to be comparable to those coming from Planck. In terms of curvature, we essentially get results consistent with a very close to flat universe. This is shown in this plot. So you see again in green the results without the shape, and in blue you see how this M parameter shape helps to break this degeneracy, and then you get like a very a result like very in agreement with flatness, and also which is very in agreement with Planck result with you're using also the lensing. In terms of an effective or dark radiation, we get that the results are not improving a lot, but yeah, there's like a mild improvement with respect to the results not coming from the shape. And we also have some results for some dark energy models, either W0 or W0 WA. These are just essentially time evolving dark energy, and this is just dark energy which has an equation of state different than -1, sorry. And we again see in each of these cases how adding the shape help us to improve the constraints. So in the last maybe 10 minutes I'm just going to be talking about the H0 tension and how the shape can help us to show some light in terms of this tension. So for those who are not very familiar, we have essentially two sets of measurements of H0. They are different and they are very discrepant now, around between 4 and 5 sigma discrepancy. So one of them is coming from a late time direct measurement of H0 by observing nearby supernovae and calibrating the distance of this supernovae with Cepheids, which is called the distant ladder technique. So you essentially start calibrating from nearby Cepheids to more distant Cepheids, and you end up calibrating the supernovae, and the supernovae tells you about how the expansion of the universe has been going in this recent years. So it's a very local and a direct late type measurement, a very model independent. And this tells you that the H0 value is around 73. Of course, this way of measuring H0 is model independent, but relies on understanding very complex astrophysical processes. So it could be that there is some hidden systematics hidden within dust, Cepheid variability, environmental dependence of the Cepheids, etc., or the team, the SHOES team, which is like one of the teams measuring this, have been like doing a very careful examination. They haven't found any. And then on the other side, you have the measurement coming from CMB anisotropies, essentially Planck, which is model dependent. They need to rely on standard lambda CDM, but even if you relax dark energy and you assume WA, W not lambda CDM, you still get like essentially the same measurement of H0, which is around 78, 70, 60, 68, 67. And of course, this is not a direct measurement because you rely on the measurement of the CMB, which is very far away from us, it's a redshift 2000. But the physics there should be well known if there are no exotic species that we haven't discovered yet. So yeah, it's not a direct measurement, but the physics should be better. And then what is the role that large scale structure plays? Is large scale structure in agreement with this guy or with this other guy? So what you can do is you can look at the BAO. We have said that the BAO doesn't actually measure H0. It measures H0 times RS, where RS is the size of the horizon scale at CMB times. So what BAO actually determines is this band over here in this H0 sun horizon scale parameter. So you can be in agreement either with the distant ladder or with Planck, depending on how you calibrate your sun horizon scale. So you can calibrate the sun horizon scale using Planck information, and obviously your result is not going to be independent from Planck. So because you want to be independent from Planck, because you want to essentially have an extra measurement of H0, which doesn't account on Planck, you can actually calibrate RS using this equation, which essentially assumes that the expansion at early times, just before recombination. It's according to lambda CDM. There is no exotic species. And by knowing the baryon abundances coming from big bang nucleosynthesis, then you can have a measurement of on H omega baryon H naught, and then you essentially can compute this. And this is what's called the BAO plus BBN technique. And this is shown in this dark blue area. So you see that you get a measurement of H naught of around 67, which is in contradiction with the distance ladder. So this technique, the BAO plus BBN, is called the inverse distance ladders, because you calibrate your measurement not according to the distance ladder technique, which is coming from redshift 0, but you calibrate it at very high redshift through the sound horizon scale at redshift 2000. This is what is called the inverse distance ladder. So you can wonder whether, okay, if I relax the conditions of my model, if I allow for an open WO, WA, lambda CDM, whether this changes at all, and the answer is no. You still get measurement of H naught very inconsistent with the distance ladder. So what's the problem here is that, yes, this measurement is independent of Planck measurements or CMB and isotropies, but it depends on assuming that you know the physics of pre-recombination in terms of sound horizon scale. So you need to assume that the expansion goes through radiation domination era, and there are no any exotic species that messes up the size of this horizon scale. Otherwise, if you can put whatever exotic species here, then you can force the horizon scale to be less than what you should get from lambda CDM, and then BEO would return you a value which would be inconsistent with distance ladder. So then the question is how the shape can help us with all this mess. And this is my last slide, is a work in progress with my no longer student, now postdoc in Edinburgh, Samuel Breeden. And let me guide you through this maybe bit of complex plot. So let's start with the simplest case. So if you remember the ratio of the BEO along and across the line of sight, we have called it FAP. I've told you that this is a constraint on omega matter, and this is shown in dotted gray lines. So you hear from FAP alone, you can constrain omega matter, not very well, but okay. It's around an error of 0.1. You cannot constrain H at all, so it's totally degenerated with H. So next step is to add the isotropic BEO, but in order to not add information in terms of horizon scale, I'm just going to be adding ratios of the isotropic BEO distance between different redshifts. And this is what I'm referring as this solid gray line. If you do so, because you don't have information on the sound horizon, you cannot calibrate your measurements, and then you cannot constrain H. So you still get like a very degenerate or completely degenerate in terms of H, but you get better constraint on omega matter. Then you can say, oh, and now I'm going to assume that I know the value of sign horizon scales through assuming that I know the physics at early times, and by assuming I know the abundances of baryons through big bang nucleosynthesis measurements. And this is what is just the BEO plus BBN that I've just talked before. And then you get this CN constraint here. So you get, essentially, you have a degeneration along this line of sight, and then calibrated with the sign horizon scale plus BBN, then you get a measurement of around 67, which is what I've described before. Of course, this relies on assuming the physics of the early universe. But you can do, okay, let's try to constrain this, assuming M, so the shape. And I've told you before in lambda CDM, the shape constrains the omega matter H square quantity, which is represented by this dashed line. So M constrains something along this line, which is represented in pink bands. And of course, when you combine M with the uncalibrated BEO, either assuming different redshifts or not, which is the orange, or the Bordeaux color, you get something in between here. So it's very interesting because these constraints coming from these lines doesn't assume anything about the sine-Erasmus scale. You still need to assume BBN, so you need to know about the amount of baryons in the early universe, essentially because the shape is very degenerated with the baryons, because the size of the shape it's related to the baryon suppression at early times. So therefore you need to know, you have to assume some measured amount of baryons, but you don't need to assume anything about the early time physics in terms of sine-Erasmus scale. And without assuming that, you still get something which is very consistent with the measurement that you get from the other side. So in other words, these two lines, the red line and the blue line, didn't have to cross if lambda CDM were not the true underlying model, but they do cross. So this means that this is like a very strong test for lambda CDM. And eventually, if you combine everything, then you get these dashed blue lines. But again, nothing that really made us these two constraints relying on very different physical process cross, and they still do cross. So this is an upcoming paper that hopefully will be published soon. And this was my last slide. So just let me go very quickly through the summary. So I have presented the ShapeFit, which enhanced the galaxy clustering information beyond the physics of BAO and RSD. And the information content is essentially coming from the broadband shape slope. So this technique has been successfully applied to SDSS data in the range of 10 billion years, from redshift 2 up to redshift 2.2, including higher redshift coming from Lyman alpha BAO. And there are improvements on extensions of lambda CDM models when no CMB data is combined with respect to what you get from using only BAO and RSD information. So this new approach allows to determine age without assuming the physics of the horizon scale as a standard ruler, which acts as an extra test for the lambda CDM. And again, these two age measurements, if you want to call age equality, the one coming from the shape and the other age horizon coming from the BAO, they agree very well within the low age regime values, so around 67, 68. And hopefully we will soon see these new techniques applied to DESI data that it should be public on the second half of next year. So yeah, thank you very much for your attention, and I'm happy to answer and clarify all the questions you may have.
Okay, many thanks, Hector. Super nice presentation. I have a few questions, but I can see some raised hands. Wendert,
yeah,
you can start with the questions.
Yeah, thank you, Hector, for the very nice talk. I have a curiosity. When you were showing the quasar linear formula, you say that when you have like extra component monopole, the isotrope feature, you can use that to break some of the degeneracy between bias and F sigma 8. And so I was wondering if you said you can even break the extra degeneracies if you added like assuming GR, then you can get information on sigma 8. So I was wondering if it's possible to keep adding extra multiple, so then you can eventually break the degeneracy between F and F sigma 8, and then instead of assuming GR, we would be able to test for GR. So I'm not sure if it was clear, but yeah.
I can comment on this. So this is just a very simpler toy model just to motivate why my natural variable was F sigma 8 and not F and sigma 8. At linear level, it's a perfect degeneracy. It's true that if you go to, so according to this model, you cannot go to higher order multiples because these multiples are 0, but you know that this model is not true. It's just a linear model. So in reality, we do apply nonlinear corrections, and this is what I call TNS model. So these models have nonlinearities, and these nonlinearities depend on F and sigma 8 differently. So in principle, yes, you can break the degeneracy between F and sigma 8 if you go to nonlinear scales, but this break of degeneracy is not going to be very strong. So it's very difficult to break this degeneracy if you go to nonlinear scales. You really need to go very further in the nonlinear regime. However, another way to break this degeneracy is to add bispectrum information or three-point function information. This information, even at first order, which is called tree level, it's not linear because bispectrum is non-linear by definition, but the first correction, the tree level, it depends differently on F and sigma 8. So if you add the bispectrum information to your data vector, you can treat F and sigma 8 differently, and then you can break this degeneracy, and therefore you can test for GR. Yes.
Okay. Yeah, I also have another question. At some point, you say about template cosmology or reference cosmology. So is there any difference between those? And a follow-up question that is if you have assumed like a cosmology beforehand, how can you argue your model, your analysis will be model independent? So could you elaborate on that, comment a little bit?
Yes. So what I call reference cosmology is the cosmology chosen to convert redshift into distances. So this is done beforehand, and well, I can discuss afterwards whether the assumption of this or not is relevant or not. Then template cosmology is when you are doing your compressed based analysis, you assume a cosmology to build a template, and then allowing physical variables to vary, you modify the shape of this template. So you can think of that your analysis is not model independent because you need to assume a reference cosmology. But in reality, this reference cosmology is just a reference. So it's like saying, okay, if I am here, how far away data is from here, and then measuring how far away from data is from here, then I can say how data really looks like. If you were choosing a different reference cosmology, then you would be either closer or farther away from data, but you would have like a different parameters. What is important is that independently of the reference cosmology you choose, either for the reference cosmology or for the template cosmology, that your physical measured variables doesn't change. And we have tested this with very different cosmologies that are even very disfavored by Planck best fit. And we always see that essentially this is the case. For the BAO is very clear because you are actually measuring the BAO with respect to a certain reference cosmology. So you are essentially just looking at how far away my BAO peak is from this whatever BAO peak I have. And then you just measure the relatives. You're always saying about the relative, but the size, also the choice of the absolute value, it's totally irrelevant. It's just, you just have to do it in the same way that you have to choose the units for solving a problem. So you can choose kilometers or meters to solve a problem, but the answer is not going to depend on this choice. So in a way, I see it in this way. It's just choosing the units of your problem, but then your answer is not going to depend on that.
Okay. Yeah. A final question, if I may. Not a question. Could you maybe clarify a little bit the formula that you show when you were talking about the M shape fit parameter? How could you? Yeah, I'm not sure if you understood this formula. How did you get there?
It's a sigmoid. So what I wanted to capture is like, if you see here, it's like, so if I choose like a fiducial, I choose a fiducial template. So my fiducial cosmology, I just take one, doesn't matter which is. And then I vary the actual true, I vary the power spectrum using CAM, for instance, and then I choose different values of omega matter, and then I plot the ratio. And then the different colors show the ratio of different of what you get. So the colors are just the ratio between a reference cosmology if chosen and a set of cosmologies with different values of omega mater, omega baryon, and NS. So what I wanted to do is to capture this variation. So I wanted to complement my template so that I can capture this variation. So this is actually a sigmoid. So you can sort of think of a way where you, by varying m, you capture these variations on omega mater. And for instance, these different dashed lines are different values of m. So you see that essentially by varying m, you capture the variation of omega mater, omega baryon, and NS. It's not perfect, so there are like slightly differences, especially for omega baryon, but I'm not very worried because omega baryon is essentially non-constrained. For NS, it's like it's perfect. So this is totally captured by this variation of M2. But essentially, I wanted to capture omega mater H square, which is this small omega mater. And it's like a random choice. All the choices could have been made, but this is just a functional form. What is important is that later I interpret my M parameter knowing where it comes from.
So maybe there is yeah, I'm not sure. Maybe there is another shape function that might be more sensitive to how the shape that you choose here would impact your result. Like if they can add extra constraining, or that's not possible. I'm not sure. I'm just thinking.
I mean, in terms of information content, I think we have demonstrated that this shape, it essentially captures all the information. Mm-hmm. The blue is like the reference full information. So this is like direct fit to the power spectrum. So I think this sort of demonstrated that at least for lambda CDM, this functional form works. But of course, other are possible. This is just something capturing this sort of behavior, but it might be like different functions. But in the end, what is important is you have to interpret M, assuming that M has been measured with this functional form and with this essential value. So if you change any of these, that's fine. You will get a different M. But when you interpret this M in terms of a model, knowing this M has been measured at these functions within this special formula, then the result should be the same. It should not change.
Okay. Okay. Thank you.
Okay. Thanks, Wendert. I don't know if we have questions. I cannot see raised hand, but actually, there's a question from YouTube from Rodrigo Gonçalves. Actually, there are two questions. I will read them here. So, regarding the SDSS3 results, specifically about the monopole signal, it seems to me, by eye, that the monopole signal shifts to the right for higher redshift intervals. Is that right? If yes, is that expected?
Sorry, I guess it's referring to this plot, but I'm not sure. It's shifted to what? It's like so okay. So let me describe very. So the lines are the best fit model. The dots are the measurements. These are different redshifts. So yeah, I don't know. I mean, this is the residual between
yeah, I think it's of the result of the parametric constraints.
So here, no,
no.
So do we know which slides?
Yeah. So Rodrigo, if you are there, please.
Sorry. Can you repeat the question, because maybe I
will. Regarding the SDSS3 results, specifically about the monopole signal, it seems to me by eye that the monopole signal shifts to the right for higher redshift intervals. Is that right?
Right. So I'm not. I mean, I'm not sure what he means by the monopole, because the monopole signal is this. I mean, for higher redshift intervals, it shifts to the right. I mean, I don't know. I mean, yeah. I mean, you can. I mean,
Okay.
yeah. So,
I
sorry,
mean, I
sure
said,
I understand.
Rodrigo is a professor here in Rio de Janeiro. I sent him the link, so
Okay.
if he can enter and ask the question. Actually, there's a second question as well. It's still on this plot, okay, but don't know exactly which plot. Are the widths of the curves around the peak equal for different intervals? Would be possible a similar analysis as supernovae with a relation between peak height and curve widths? Okay, sorry, it's not very clear for me.
So it's not. I'm not sure what's the question. Sorry, really.
Okay. I sent him the link if
Okay.
if he can
Yeah.
enter. He will. I have some questions. Let me take advantage of the Wender's question on this M parameter, and you mentioned at some point that M1 and M2 they are degenerate.
Right.
Yeah, I was trying to figure out, try to understand why this degeneracy appears. I mean, when we talk about matter-pole spectrum, the NS affects the matter-pole spectrum as a global tilt, as well as in CMB and omega m. This lower omega m, which is this omega m times h squared, works in different aspects of the matter-pole spectrum. How could I understand this degeneracy between these two parameters? I think yeah.
I think it's. I mean, if you think within lambda CDM is sort of easy because, well, easy. I don't know. So you have NS essentially determines the slope of your scale invariant power spectrum, and then this is like essentially a power law, and then you have. I mean, if you assume that you have the omega variant fixed, then you know that there is this turnaround that are essentially the modes entering the horizon at different epochs and then growth being suppressed. And then you have this turnaround thing around K of 0.1. And this is very sensitive to omega matter h squared. So you have here two effects, which I think is what you measure is the slope, and the slope is sensitive to omega matter h squared within lambda CDM. But then this slope, essentially, you don't know whether it's a global slope, which would be M2 or NS, or it's actually the slope caused by the modes entering the horizon and therefore their growth being suppressed. So you have like two processes where in this range of scales that we measure, which is essentially from 0.01 up to 0.15 or 0.2, these two effects are very, very difficult to disentangle. If you had access to scales very much, I mean, either smaller and smaller scales, and you knew how to model biases there, or you had access to very, very large scales, then you might be able to break the degeneracy. Also, if your measurements are very precise around these scales, in principle, you're also going to be eventually going to break this degeneracy. But I mean, you're not going to break the degeneracy. The degeneracy is going to always exist, but at least maybe the error bars are going to be something tractable.
Okay, I see. That's perfect.
I mean, essentially, you can see it somehow in this way, right? So if you forget about the lines, the dashed lines, right? So a variation of omega matter produces this change of the slope in this ratio, and a variation of NS produces this. So it's true that this is not exactly this, because you know there's a bit of curving here and curving here, but it looks very similar, especially if you consider a range of scales which goes up to here, so from 0.15 or maybe 0.2 up to 0.01. So it's very difficult to disentangle. So you see here that both, they are very degenerated. You don't know. You don't know. Yeah.
I see, and as well, if we include error bars and so on, I see.
Exactly. Yeah.
There's something you mentioned at the end that you basically can apply for this kind of lambda CDM extensions, and I mean that's why you call this agnostic, because the measurement it's independent. But is there any kind of limitation for modified gravity theories and another super exotic alternatives to lambda CDM model?
Right. So it's true. It's model agnostic, but still it has something in mind, which is lambda CDM. So for instance, for modified gravity, well, modified gravity doesn't mean anything and means everything at the same time, right? Because modified gravity is anything which is not GR. So for instance, for modified gravity theories that they have a scale-independent growth factor, obviously this naturally works because you have a measurement of F independent of omega matter, so there's no problem in there. If you have variations of F with the scale, then it's true this parametrization won't naturally work. Then you would need to modify these and introduce maybe changing slope between large scale F and small scale F, and then try to measure whether this slope between these two regimes is something different than zero. That would be like the natural way to extend this to like a non-GR scale-dependent growth factor theory. In terms of the shape, which is the new parameter here, if you want to constrain like an exotic model that have modifications of the transfer function, well, not modifications, let's say, that have very distinct features of the transfer functions, like it has like an oscillatory feature of the transfer function around the scale where M is measured, then obviously this won't work. Or in other words, I mean, this always will work, but it will not work in an optimal way, because this M will always capture some effective measurement of the true underlying transfer function. But obviously, if you are interested in capturing the features of this, imagine, oscillatory behavior of the transfer function there, then M is not suited to do so. So you would need to modify your template in order to sort of parameterize these features you want to observe over there. So obviously, there is no model agnostic parameterization that is optimal for any potential model, cosmology model that you can imagine, but at least it works in an effective way.
Okay, thanks. Okay, my very final question. You mentioned at some point that we should not be worried about this difference between full modeling and ShapeFit, because the surveys we have today, they are not able to capture such a small difference.
Right. So you mean
I mean, my question is, how accurate must be a survey to be able to capture a difference in that sense? I mean, will DESI be able to do something like that in the future, or we could stay using ShapeFit for a long time, at least?
Right. So yeah, this is an effective volume of 566, which is larger than any effective volume can be measured because the universe is not so large. So in that sense, DESI will reach maybe between 25 and 50, depending on how you quantify this, but obviously this is a different redshift, so it's a bit tricky to, because they are like degeneracies that are broken, so the error bars won't decrease just with the survey area, because they are like measuring high on redshift, it will break degeneracies. But in any case, this is like a very large volume, and these differences, they are never going to be detectable. However, one of the challenges is to use smaller and smaller scales. So here I'm just using up to k equal 0.15. If you go to smaller scales, then these systematic error bars change. So you get like tighter constraints. So your statistical errors are better constrained because you're using more information. But because you're going through the nonlinear regime, then your perturbation theory models at some point stops working and then stops deviating from the truth. So there is a bit of trade-off. So if you want to, so in terms of, if you are conservative and you want to stay up to 0.15, then at least for lambda CDM, this model, this is super safe. This is never going to be reached by any survey volume because there is no enough galaxies in our universe to reach such precision. But I mean, if you go to smaller scales, then the thing changes. So, and obviously, this is just a, to be honest, it's a toy model example. So this is, I mean, we have here a 3-parameter model, but here we know which is the omega baryon value true. We know which is the NS true value. We more or less know how the galaxies populate the halos, and we know that there is nothing weird going on there. So I foresee that the challenges are more going to either model the nonlinear scales and make sure that the galaxies we are using as a tracers, they have galaxy bias that we understand and we have under control.
Okay, thanks. So does anyone want to ask questions? Okay, so let me thank you, Hector. Thank you very much. Your seminar was very pedagogic and very nice for us.
Thank you very much to all you and for paying attention and stay with me this whole hour. And if you have any other questions at any moment, just please drop me an email and we'll be more than happy to answer all your questions.
That's great.
Thank you.
Okay.
Thank you.